All right, so this is Lab 8, Part 2, and we're moving from Part 1 where we collected data, we took a look at the data, we took a good guess at whether it was discrete or continuous to give us a good idea of what family of models that we'll need to fit to the data. And now it's nice to have a tool to help us with that fitting. And so ARENA provides an input analyzer, and so in this video I'm going to go through the basic steps of how to get your data into the input analyzer and to use the input analyzer to perform those fits. Now before we can get into the input analyzer, we need to get the data into a format that the input analyzer is comfortable with. So if you're in Excel, like this image here, and you've got a data set like this simple data set here, what we're going to need to do is save that data as a single column text file, particularly an MS-DOS formatted comma-separated values or CSV file. We're going to make sure that the encoding is not UTF-8. So a lot of new programs are perfectly fine with UTF-8 encodings. The input analyzer, at least for now, is not. And it's got to have MS-DOS formatted line endings. It'll still work pretty well without the MS-DOS formatted line endings, but there's a couple of small convenient features inside the input analyzer that if you don't have the MS-DOS formatted endings aren't going to work well. So you got your data file, you've put it into a single column, so then you go to File and Save As, and under your file format it might default to, well, it'll probably default to an Excel workbook or an Excel workbook up here, XLSX, if you're using Excel, or something similar inside Google Sheets. But then under common formats, you might see this CSV, comma-separated values, but it'll say UTF-8, and you want to avoid that UTF-8. ARENA will not know what to do with a UTF-8 encoded file. So instead, let's go under specialty formats. And you'll notice there's comma-separated values, there's Macintosh comma-separated values, MS-DOS comma-separated values. If you're on a Windows machine, you might just see comma-separated values. The big thing is just avoid UTF-8. And if you can find the MS-DOS comma-separated, that's the one that's the safest choice. So that's what I've chosen here, MS-DOS comma-separated values. And I'll save that as a CSV file. In the old versions of ARENA, you actually had to save things as the DST extension. So you got to get rid of the .csv extension and replace it with .dst. But in newer versions of the input analyzer, it seems to be okay with the CSV. So once you've saved that data out, you can go into the input analyzer. There's two ways to get into the input analyzer. The first way is if you've already got ARENA open, you can go to the Tools menu inside ARENA, drop down, and you'll find the Input Analyzer underneath there. Alternatively, if you're in Windows and you were to go into the Rockwell Automation folder in the Start menu, or you were just search, if you were to type in ARENA Input Processor, it's a little weird, it's not Input Analyzer, even though that's what it's called up here, then that will also start the Input Analyzer. Either way, that'll pop up in the input analyzer. There's not much to see initially. It looks a little like this here. So go up to File and then say New. Once you do that, then again, there's not a whole lot to see, but you got to go back up to the File menu here and then go down to Data File. And then from Data File, select Use Existing. And then from there, so notice I didn't do File Open. You're going to be tempted to do File Open, but instead you do File, Data File, Use Existing. And then from there, that'll open up a browse window, and then you can open up those files that you just saved. So here I've got them ending with the file extension DST, but again, in the newer versions of the input analyzer, it should open CSV files, but just make sure it's not UTF-8 encoded, and then hopefully it has the MS-DOS line endings. That will help with later portions, but even if it doesn't have the MS-DOS line endings, it still should open so long as it's not UTF-8 encoded. So then we open that up, and if they don't show up here, you might need to go down to Files and Type, and if it's looking for a DST file, you might be able to generally select text files or all files, and then hopefully they'll pop up. All right. Now once you've done that, it should pop this up here, and you should see your data. It populates a histogram. We'll talk about that in a second. So you've got your data here from Excel, and you've got this histogram in the input analyzer. Just for confirmation, I can go up to the window menu inside the input analyzer and go down to input data, and it will then show me this list of data here. And look, they match exactly what I saw in Excel. So that's a quick way for me to look back at my raw data. And if I forgot whether my data was discrete or continuous and those sorts of things, then maybe taking a look here will help with that. Now, if you happen to notice that all of your data seem to be on one line with no separations in between them, then you probably didn't save it as an MS-DOS formatted file. It doesn't have those MS-DOS line endings. And if you were to go back into Excel or whatever spreadsheet program you're using and resave it with those MS-DOS line endings as an MS-DOS CSV, and then to go through this process again, then it'll show them nicely here with them separated out. All right, so now let's just stick inside Input Analyzer. We're done with Excel. And so what we see after we've loaded our data is it automatically generates a histogram. It picks the number of bins based on some heuristic inside the input analyzer. We'll see how to change that. And then it gives us some summary statistics. So it can tell us there's 10,000 data points. The minimum is around 0. The maximum is around 0.9. The mean is 0.2, and the sample standard deviation is 0.15. So if I don't like the histogram it did here, I can go up to the options menu, go down to parameters and then histogram, and I can tell it how many bins I want. And I can tell it where I want the edge of the lowest bin and where I want the edge of the highest bin. And those things are summarized down here as well. Now, to get more into the real value of this program, if you go under Fit, you'll notice a number of distributions that hopefully have names that are familiar to you. If you then select one of those, it will then generate a best fit. So here I did fit, and then I went down to gamma, and I selected that, and it tried to give, so it showed me this is the best fitting gamma distribution to these data. And it will estimate the best parameters here, so I can see these parameters show up here. It shows me the squared error, which is a measure of how good this fit is relative to the actual data. And then it'll actually end up doing a chi-squared test, where it actually does picks all of the parameters correctly for it to set up this chi-squared test, and it shows me the p-value coming out of the chi-squared value, as well as the actual chi-squared value. So note here that this fit is a bad fit. So even though visually this might look like a good fit, with as many bins that we have here, and with the distance between these bins and the expected count for those bins for a chi-squared, our chi-squared statistic is far too high for this degree of freedom. And so the p-value is going to be less than 0.05. So remember, a low p-value is a bad fit. Just because it looks like a good fit to you visually doesn't mean it's a good fit. So look down here. A lot of times I have students, when they finally present at the end of the semester, actually forget which one's good, a low p-value or a high p-value, and they'll say, look how great this fit is. It has a really low p-value, and visually it looks great. When actually that really low p-value shows that even though visually it looks great, statistically speaking, it's not actually doing a very good job. Okay, so if you look down in the distribution summary, you'll also notice there's a line that says expression. And that expression, there is actually a SIMAN expression that you can use in ARENA. So the idea here is if you end up liking this fit, even though we've already said this is a bad fit, but if you end up deciding that this input model is the right one for you, you can actually just copy and paste the expression that's right out of here, and that includes the best fit parameters as well as the ARENA code, so you don't even have to look up the syntax. And so all that's already done for you. Now sometimes there are additional parameters in here that you wouldn't normally associate with that distribution. For example, a beta distribution, if you're not familiar with a beta, is a continuous distribution between 0 and 1 that has a lot of flexibility in the way in which it can be multimodal, it can be skewed to one side or the other, but it's got this finite support between 0 and 1. And so a lot of people like to use a beta to represent other types of things that have bounded intervals, let's say going from 0 to 50 or from 49 to 53 or something along those lines. And so what they'll do is they'll stretch the beta so that its outcomes are scaled and shifted to the interval they want. But ultimately, underneath it all, it's still just a beta distribution, which is kind of distributed between 0 and 1. Now, the two normal beta parameters, this 1.49 and this 5.42, those correspond to an interval of 0, 1. But there's an additional shift has been added. It's multiplied by 1, so it's still only as an interval of length 1. But then it's shifted up so that it actually, these outcomes will come out from 5 to 6. And so the input analyzer is smart enough that if you say fit beta, and it looks at your data and it says, wait, your data aren't distributed only between 0 and 1. They're distributed between 5 and 6. It will automatically add those additional parameters to shoehorn that beta distribution so that it can better fit your data. And then once it's got the range correct, then it'll pick the other parameters to get the shape of the beta distribution in between correct. And so look out for those parameters as well, and be careful when you're copying this expression into Arena that you capture all of that. And also when you're reporting these expressions to me, make sure that you don't just say, oh, it's an exponential distribution, if it's also had this kind of additional shift added to it. All right. So if, like I was saying about these parameters, once you do the fit, they're set for you automatically. But if you would like to see what other parameters might look like, you can go up to the options menu, go down to parameters, and instead of going to histogram like we saw before, you can go down to distribution. And then from there, you can actually edit these parameters. And if you change the values here, then it will then reevaluate the chi-squared test here for you to evaluate exactly how bad or how good those parameters are. So if you might, if you think about, say, homework G3, in one of those exercises, we might tell you ahead of time what the mean is. We say it's not just a Poisson distribution, but it is we think hypothetically it is a Poisson distribution with mean 3. Well, then you can actually go in and evaluate how well a Poisson distribution with mean 3 is inside here by manually adjusting these distribution parameters. But remember, you have to go to the fit menu first and have it do its own fit before you can go to option parameters and get access to these. Now, I've mentioned that it does a chi-squared test. Now, we've seen KS tests, and sometimes we want a KS test. It can do a KS test as well. So, if you go under options and then under data fit, then in the data fit options, you can check the include KS box, and it will then add a KS test underneath here. But it can't do that if you have a whole lot of data. So it really only is able to do that for relatively small data sets. Once the data sets get very large, then it just doesn't even bother with the numeric or the computational burden of calculating a KS statistic. And actually that's probably okay, because once you have a whole lot of data, you may as well use a chi-squared test, because that's exactly the situation where a chi-squared test is going to work well. Now, rather than fitting every single distribution manually, under the fit menu, some of you may have already noticed that there is a fit all. If you select fit all, it will then find the best fitting distribution of the ones it has access to, and then show you that one here. So in this case, the best fitting distribution is a beta distribution. The squared error, if you can see it under the red line, is very low. And the chi-squared has a p-value, which is definitely not rejecting the beta. So we can't say for sure that these data come from the beta distribution, but given how much data we have a pretty good idea that we have enough statistical power to conclude that a beta probably is a good fit to these data. So a lot of you are going to want to do fit all. But I'm just going to caution you that when you do that fit all, sometimes the choices it makes are going to be not necessarily the best informed choices. So it really likes to fit, for example, gamma distributions or Weibull distributions. And that's because gamma and Weibull distributions both are very flexible So they can generate distributions that look pretty symmetric. They can generate distributions that have a lot of skew. So they have these two parameters, and these two parameters really allow you to stretch and skew these distributions all over the place. Now, I think you should only use, say, a Weibull distribution if you have some insight that there's not a better distribution. So, for example, if your distribution looks pretty exponential, but it just so happens that a Weibull is a slightly better fit, but you have some insight that the, say, inter-arrival times you're modeling are independent from each other, then even though the Weibull might be a slightly better fitting distribution, it might be better to go with the exponential. Not only because you have insight that the exponential might just be the better distribution, but it also is because that distribution has fewer parameters. And it's always better to select a model that has a really good fit with fewer parameters. And so that's kind of all that I'm saying here. If you go to Window and Fit All Summary, after you've done your Fit All, it shows you all of these distributions it tried to fit, and it shows you all the squared error terms that corresponded to them. And if you find that the best fitting distribution has a similar squared error to other distributions, especially one that has a lower number of parameters, then it might be better to use that other distribution. So if there's one that just dominates in terms of squared error, then maybe, yeah, that's a good one. But if there's 3 or 4 that have almost the exact same squared error, then I'm expecting you to use your modeling insight to choose the best among those, and not just the one with the slightly smaller squared error. And if you're not quite sure, if there's a distribution that has fewer parameters, like 1 parameter instead of 2, but nearly the same squared error, go with the fewer parameters. Now, what if there's no distributions inside ARENA or inside the input analyzer that work for you, that all of them are bad fits? In that case, you might want to go under Fit and then go to the empirical option. And what that'll do is it'll generate an empirical CDF, and then it will then automatically generate an expression using either cont or disc. That's up to you. It gives you both options based on that empirical CDF. Now, I want to list, there's a little caveat here. It builds its empirical CDF based on the histogram. So it converts the histogram into the CDF rather than using the raw data. So if you have histogram parameters that, say, have a lot of very wide bins, or very few bins that are very coarse, then you might end up wanting to go into those histogram settings first and then adding more bins before you do this option. So that's under Options, Parameters, Histograms. So again, make sure you're comfortable with where these bin locations are before you do this empirical CDF, because these outcomes here are going to be the locations of these bins. They are not actually going to be outcomes that are in your real data. Now, if you are sure that you've got discrete data, you still can use the input analyzer, but it's really limited in how useful it is. If you know you have count data, you can go to Fit Poisson, and it will give you the best fitting Poisson. But the thing is, if I look down at these data here, I can see the sample mean for these data is 7.04, and the Poisson expression is in 7.04. What you're going to find is every time you do Fit Poisson, it's just going to do a Poisson distribution with the mean from your data. And so I didn't really need the input analyzer to do that, because I could just take the mean and try out my Poisson anyway. It does tell me, though, like, it will give me the chi-squared output, which I guess is kind of nice. In this case, I reject the Poisson. Now, for other discrete distributions, I would really hesitate for you to do much in the input analyzer. Again, some people are going to be tempted to do Fit Empirical, and they're going to try to use the disk line that comes out for that discrete distribution. But the downside of doing that is it is not going to use your raw data. It's going to use those histogram outputs. And so your raw data might have outcomes like 0 through 10, but it might bin them for some reason, where 0 and 1 get binned together, 2 and 3 get binned together, 4 and 5 get binned together, and so on. And then your outputs are going to be these coarse bins. They're not actually going to be the real outcomes that you see in your data. So I really hesitate to do fit empirical with discrete data. I really would only do that with continuous data when there's no other option in this list here. If you got discrete data and you don't know what family to fit to them, then maybe you should just manually calculate proportions in Excel or MATLAB or R or whatever. So again, empirical, you can always adjust those histogram parameters that are option parameters. I just want to keep hitting you over the head with that. If you're going to use fit empirical, make sure you're happy with the histogram, because you're effectively using the histogram and not the raw data. All right, the other thing that in the input analyzer can do is it actually can sample from these distributions for you. So rather than you having to build using, say, the inverse transform method, your own inverse transform sampler, you can go in, and if you do file new and then file data file generate new, any one of these families here, including some that you haven't seen yet in the fit menu, like Johnson, if you select them, you can then put in a set of parameters. You can tell it how many data points you want, and then you can fill in the data file, and from that data file, it'll then generate a data file of sampled data that you can then go and actually reanalyze inside the input analyzer. And so it's a way that if you want good hypothetical data, you can generate it this way. There are even ways for you to take these hypothetical data and feed them into Arena. Let's just say, for example, you're building an Arena model that you want to use with real data that you've gathered from your system, your restaurant, your airport, whatever, and you haven't actually gone out and taken that real data that you want to feed into your simulation instead of drawing it randomly. Well, you can then generate fake real data inside the input analyzer, and that way you can test whether your coding works and then feed these right in. All right, so that's the end of the input analyzer tutorial. In part 3, which will be a shorter video still, we'll go over the exercises that you're expected to do here in Lab 8.